I'm going to give you an algebraic perspective on deep learning. And like any good mathematician, I'm probably going to spend this first hour mostly defining what my terms or giving you, in order to think about deep learning in an algebraic way, I have to understand the models that you use as mathematical objects. And so what I'm mostly going to talk about today is some ways that we think about, in people in applied algebraic geometry and related areas, think about models like those used in machine learning. And hopefully there'll be some insights that come out of that. So the motivating questions for me are questions about things like representational power and performance. So performance is harder, but at the very end I'll talk about some ways that we can get at that. Representational power is something that we're very comfortable studying. So we're good at characterizing representational power because we have a precise way to define what it means by how to answer questions like, what can a deep learning model? So what are the space of probability distributions and what are the space of functions that it can compute? And how well it can do that. We'd like to do things like bound errors in approximation, prove convergence, prove any kind of property you might like to study. And the idea is to try to systematize what's usually done as an engineering problem, right? Where we try different things, we figure out what works. We'd like to be able to try to provide theoretical reasons why certain things should work, or why you should try some model first before you try others. So in other words, we seek a priori design insights. We'd like to know what, given some assumptions about the data, what model architecture is going to perform best for that. And that's a hard thing to know ahead of time, but we always know some things, right? So if we precondition our pre-whiten or do some other thing to our data before we input it, that means that we know something about the class of distributions for which our model works. And we'd like to get deeper insight into that kind of problem. A way to know that you were successful at that is if you can actually predict performance, right, beforehand, before an experiments happen. And we want to be able to understand what trade-offs there are to make, what trade-offs should we make, what kind of, in which cases are, for example, one model strictly better than another model? Like what kind of partial order can we put among things? And we want to understand the representations that we obtain after fitting a model. And statisticians call this identifiability. So when do we know that a unique set of parameters came from best explains our data, or a unique set of parameters up to some action of a group, or some other a notion of approximation, and that also leads towards ideas of the hopes for transferability, right? So if we have many different sets of parameters that give just as good performance, if we can understand how those parameters are all really examples of the same thing or in the same orbit, then we have a better chance of transferring what we've learned from one model to a different model that doesn't have the same architecture. And so my goal is to describe some algebraic approaches to these types of problems. And there's going to be 3 parts. So today's part is the algebraic geometry of tensor networks. And as promised, I'll mostly just define the terms in that phrase. So tensors, tensor networks, and algebraic geometry. And then tomorrow I'll talk about applying that to create algebraic and semi-algebraic descriptions of graphical models, and applying that to restricted Boltzmann machines and deep belief networks. For many submodels of these things, we have a really good understanding of what it is algebraically. In some sense, deep belief networks contain many of the models that we do understand. And so that's kind of the frontier. And in the last hour, I'll talk about some of the other perspectives and the exciting new developments that are coming out of this thing. Identifiability I mentioned already, and there's this thing called singular learning theory, which tells you that algebraic geometric properties of a model can actually predict things like the Bayes generalization error. And so there's hope that understanding these things will translate directly into a prescription about which models will perform better than others. So today, algebraic geometry of tensor networks. So how does a mathematician think about these objects? So first we do tensors. So it's algebraic geometry of tensor networks. First tensors. So even before tensors, matrices. So here's a chunk of a Rubik's cube, which represents a table of numbers. And there are sort of 3 sides to this, but there's only 2 sides that are important for a matrix. This matrix represents a linear transformation that goes from the yellow vector space to the red vector space. And there's a notation for this that kind of is a process notation that has grown up in many different places. But one of the first places this has happened in is the work of Penrose in physics in the 60s and 70s. So a matrix is a linear transformation. It takes some input and it gives some output. It's represented by a two-way array of numbers, and it has some kind of group action by change of basis, by a general linear group, which acts differently on these two sides. If it's a symmetric matrix, it's the same action. And if we worry about primals and duals, maybe there's a group element or its inverse that's acting on any of these things. So it's a linear transformation, and that comes with information about how it transforms under change of basis, right? So diagonalization and all that. Of course, matrix decomposition is a workhorse of machine learning and signal processing and many other things. And so, we'd like to, if we want to understand tensors, we'd like to take what we've learned about matrix decomposition and somehow expand that to tensors. And of course, there's many ways that we already do that. And one simple way to use matrix decompositions directly is to take whatever data you have and force it into matrix format. So forget a bunch of, if I have 5 different variables, just treat it as a group of 2 variables and 3 variables. And now I have a nice two-way data set, and I can think about that as a matrix and decompose it. So a tensor is a full Rubik's cube, not necessarily the same number of guys on each side. And that represents a multilinear transformation. So now all 3 of these, the red and the blue and the yellow, matter. I can think about it as a multilinear transformation from the tensor product of 2 vector spaces, like these 2 vector spaces, to the third vector space, W. Or I can make any other grouping I want, from W to U tensor V, from U tensor W to V, et cetera. So it's a multilinear transformation. It's linear once I group it into partition it into 2 pieces. And it's a multi-way array, so it's represented as some multi-dimensional array. Here, the multi is equal to 3. And it has an action, just like the matrix has an action on each side. The tensor has an action on each side, or each leg, if I'm writing it in this notation. Right? So each possible side has some kind of vector space associated with it, and that has a space of transformations associated with it. And so when a physicist talks about a tensor field, it's very much about how it transforms, primals and duals, and how those actions develop. So tensor decomposition is a possible thing, but it's a lot more subtle than matrix decomposition. And if you just try to take the idea of an SVD or whatever from matrix land and you try to do it in tensor land, you're often going to do something which is sort of numerically nonsense. Right? You're optimizing a non-well-defined objective function, or you're sort of hoping that something will be true, and it couldn't be farther from the truth. So it's more subtle, but we have lots of techniques for doing that, and I think one of the most successful techniques for tensor decomposition is graphical models, right? For discrete data, you could think about that as a technique for tensor decomposition. Data often arrives in tensor format. There are many variables, and something is lost by forcing it into matrix format. So that's tensor. So here's an example of how things can go wrong. The eigenvalue decomposition of matrices. So if I have, say, a symmetric matrix, there are 3 possible generalizations, which are the same in the matrix case, but they're different in the tensor case. If I have a p by p by p tensor, there's something called the tensor rank, or the outer product decomposition, which is that I write this tensor as a sum of rank 1 tensors. These are vectors ui tensor vi tensor wi. So that means I just take if I have a table, a 3-way table, I just multiply these 3 vectors entry-wise, and each entry is the product of the row, the column, and the supercolumn. Okay? I write it as a sum of such things. That's very nice. In the matrix case, that's a closed set. In the tensor case, that's not even a closed set. So if you try to find the best low-rank approximation, that's not even going to be well-defined. I can take the limit of that thing, so I can close this set. That's closed, but it's hard to represent, and we don't really know that much about it. Another example of something where we know more about is the multilinear rank, which is to say, I think about the eigenvalue decomposition instead of as a matrix that's long and skinny acting on a small matrix to make a big matrix. I do that in the tensor case. I have a bunch of long, skinny things that act on the small thing, and that's something we understand better. So this is just an example of how, as you go up, things kind of break apart into things that we felt we understood in the matrix case break apart into different pieces, and we have to be careful about how we extend our knowledge. And that's why algebraic geometry becomes important, because that's sort of the study of understanding what happens when we leave linear. It's sort of the study of nonlinear algebra, if you will. So these generalization of matrix concepts to tensors is usually not a straightforward thing to do. But, flattenings are still matrices. So if we do like a flattening where we just think of this tensor as a linear map from one vector space to another, that's still a matrix. And everything we know about matrix is certainly true of that. It's just not the whole story. And most of all the effective computations we do in multilinear algebra reduce to doing some kind of numerical linear algebra, because I'm sure many of you know, much of the time you're better off transforming your problem into something you can do with vector linear algebra or a linear algebra package than trying to do it by hand. Okay, so what is, just in these sort of diagrams that I'm drawing, these funny diagrams, what does it mean to flatten? What are the basic operations? So flattening, so if I think of a tensor as lying in a vector space, which is the tensor product of 4 vector spaces. So this is a 4-way array. Each of these ways might be dimension 5 or 3 or 2 or 7. I can view this tensor that lies in this as all kinds of linear maps. And sort of graphically, I can think about that as the tensor itself is sort of starting from nothing and going to a tensor product of 4 legs, 4 vector spaces. If I take 2 of these legs and bend them up, now I can think about this whole object. If I just kind of draw a circle around it like that, it has 2 inputs and it has 2 outputs. So I think about this as a map from ZW, or technically Z star tensor W star, so the dual vector spaces, into U tensor V. So that's a flattening. Just take any tensor and view it as a linear map. And the other thing I can do is to contract. So if I had a tensor T and a tensor S, both of them have some number of legs, I can connect some of the legs as long as the dimension of the vector space is the same, or it's the same vector space really. And what I get out is some other tensor, which is just to draw sort of a bubble around that. Right? And one way to express that is just flatten, multiply the 2 matrices together, the things that you want to contract away, and then reshape the array. Right? Okay. So that was tensors and the 2 notations that we'll look at for tensors. And I want to talk about algebraic geometry of tensor networks. So let's go now to tensor networks. So tensor networks are basically things built from lots of little diagrams like this. So this is a picture, this is a stock photo from about analyzing business processes. So she's drawn something which looks a lot like a graphical model, though it's probably not exactly that. And so what is a tensor network? Why do they keep coming up? And I think that one of the reasons this happens is whenever we reason about a process in space and time, whatever that process is, probabilistic, even a quantum process, that involves interaction and independence, that involves causality, locality, we tend to draw these diagrams that have boxes and wires and arrows and things like that. And then sort of the PowerPoint representation of what's going on. Right? But if we want to make a model, we have to attach some kind of mathematical meaning to this diagram. And that allows us to quantitatively capture what's going on and to do computation on our hypothesis. And from a mathematician's perspective, this means that we're defining a monoidal category, which is a fancy word that you probably haven't heard before. So a monoidal category you could think about as the most general setting in which it makes sense to take a tensor product. Okay? And the nice thing about monoidal categories is that they're so abstract that it makes just as much sense to talk about a monoidal category that's built out of drawings like this as it does to talk about one that's built out of vector spaces and tensors. So this means there's certain notions of freely being able to draw different diagrams on the blackboard or make PowerPoint diagrams, and that actually corresponds to, there's follow certain rules that corresponds to something with mathematical meaning. And to analyze this often means defining a functor, which is something that happens in category theory, a map to the category of vector spaces and linear transformations. So that's back into what we call tensor networks. Okay. So category theory, which I'll talk about just a little bit today, just to give you your vitamins, provides a succinct and beautiful means to formalize the ideas we have about such diagrams and how to interpret them in mathematics. Mostly we'll talk about vector spaces and linear transformations, that category is often called tensor networks, drawings and the diagrams in that category. And the reason that I'm going through this rigmarole is that it turns out that a lot of the same mathematical ideas can be used to analyze these tensor networks, or these networks of drawings, these monoidal categories, whether they occur in machine learning and statistics, computational complexity as circuits, quantum circuits, things like that, constraint satisfaction problems, quantum information, circuits, many-body systems, and things like that. And the point of doing that is just that if you sort of can see them all as the same object, it gives you additional sort of horsepower to figure out what's happening and to make a formal connection between things. If I want to say, deep models can compute things that other things can't compute, well, I should really be thinking about it in terms of computational complexity, right? And if I have a very careful understanding of exactly the map between these things, then that's something I can expect to do. So algebraic geometry and representation theory are kind of the natural tools to characterize and understand these objects. And here's just some examples. So this is a deep network. Here's a Bayesian network. Here's some things how they pop up, how these tensor networks pop up in complexity theory. So this is a diagram from Penrose's paper in 1971 about tensor networks. And this has actually a picture of sort of the four-color problem. So it's a certain type of tensor network, and the four-color theorem says that this thing always has contraction or total value greater than partition function greater than 0. And they show up in quantum information as well. Okay, so here's our wiring diagram, or our funny little leg thing for tensors again. We have a multilinear operator. We have a wire for each vector space or each variable in a graphical model. We have a box for each tensor, so that's like a factor in a factor graph model. And the arrows keep track of what's the input and the output, or what's the primal and the dual vector space. I'm allowed to connect wires to compose or contract. So we talked about contracting before. If I want to write H composition G composition F, then I just plug these guys together. So first apply F, then apply G, then apply H. So unfortunately, our notation moves in the opposite direction. A straight arrow just means nothing. That's an F. And I can run these computations in parallel, or I can run these things in parallel by saying, taking the tensor product of the vector of the transformations, so that's like the Kronecker product of the matrices that represent them, run them in parallel. Just juxtapose them next to each other. And from these primitives, and maybe some other primitives, depending on what you want to represent, you can build up some kind of complicated looking network that would make the lady in the front happy. Okay, so the one takeaway from this is that these mathematical objects are sort of canonical, and there's no way to avoid them. And so if you had thought about how to model probabilistic things with monoidal categories, or how to attach a diagram to a diagram of probabilistic notion, you could have invented graphical models. So, and many people did invent variations on this thing as things like Feynman diagrams, graphical models, circuits, quivers, and representation theory, and things like that. So this is no accident and reflects this underlying mathematical structure. And we want to understand the common generalization so we can translate results from one area to another. Okay, so here's the vitamins part, 3 slides. So if you don't like it, just space out for a second. Okay, so we have a graphical language for monoidal categories. So one of the fancy ways of saying this is that a 2-category with one object is a definition of a monoidal category. You can think about it as a bunch of maps. This map A, this map C, this map B, this map D. And then there's maps between the maps. That's why it's a 2-category. There's sort of 2 layers of maps, F and G. And then I take the Poincare dual, so I replace spaces with points and lines with lines the other direction. And then I get a diagram language that looks like this. So this is F tensor G. And similarly, I can compose these maps between maps to get a tensor product like that. And papers by Joel and Street, Salinger, John Baez are great places to look to understand this stuff. So I keep talking about categories. Let me just give you the definition. A category is a class of objects. In our case, the objects are always vector spaces, and a set of morphisms for each pair of objects. So that's all the possible ways to connect one vector space to the other. Set of linear transformations. It has a composition rule that says if I have one map and I have another map, and the output of the first map agrees with the input of the second map, I can plug them together. It has an identity, which says I can leave things alone. And it has a diagrammatic language, which is, we've already seen. It's with the one line of these things. A monoidal category is this complicated looking thing. So this is a category with a bunch of extra data. It has a notion of tensor product, and it has a bunch of stuff which essentially forces everything to agree with everything else. I won't get into the details, but a lot of this can kind of be made to go away. But I thought I'd throw it up. And we can do things like, I've drawn all my diagrams in a planar way. We can do things like crossover, swap things together. And these things become important when you want to use these objects to study things like knot theory or something. OK, so that's the end of that part. So if I have a graphical language of monoidal categories, if I wanted to be, if you wanted to invent graphical models using this stuff, what would you need? So you have this graphical language of categories, which is sort of most of the way to drawing these networks that we show up. And then you can throw in some additional axioms that I won't get into exactly, but they sort of have to do with each local object having interpretation as something called a Frobenius algebra. So that means that essentially that everything has an orthonormal basis attached to it, which means, again, that all these vector spaces are not just vector spaces, but they're vector spaces equipped with a basis. The basis elements just correspond to the outcomes of the random variables. Okay? And so if I did that and I tried to figure out what the graphical language, I would get something that looks like factor graph models. So I could take a Bayesian network, I can convert it to a directed factor graph, like this is in this Frey paper, and then just a little bit more detail gives us something called a string diagram, which is how people who think about this in category theory would write it, or physics. That's nice just because if we're trying to use some of this other equipment in order to study graphical models, now we know how to represent them. And we can think of this as kind of a shorthand for this language, which can express everything graphical models can express, plus some other stuff. If I have an undirected graphical model, I can also convert it to a string diagram. Essentially, all the things which are just variables, I just make into dangling edges. And now that's just a tensor, right? So this is the sense in which here we have a bunch of dangling edges too, right? This dangling edge, this one, this one, this one. If I draw a cloud around this thing that just lets these dangling edges come out, I've just written a tensor in my notation from the beginning, right? So this is the sense in which graphical models are a strategy for tensor decomposition. Here's an example for a naive Bayes model, so the simplest model. We'll talk about this one a lot. This is a graphical model where I have some discrete hidden state. I have discrete visible states. And this is either an undirected graphical model or a directed Bayesian network. And I can express this in the string diagram notation by these things called a unit map and a co-multiplication maps, just composed with a bunch of factors. So this is the string diagram version of a naive Bayes model. And I can do other graphical model constructions like gluing triangles together, or this one. So if I start with a naive Bayes model, right, this is a very, very simple deep belief network. Right? This is a restricted Boltzmann machine with 3 visible units and 1 hidden unit. Okay, it's kind of the most possible boring one. And then if I want to make a real restricted Boltzmann machine, I just glue a bunch of these things together along the bottom. And so that operation is I would call a Hadamard product of naive Bayes networks, and it can be implemented by using the multiplication in this type of category. Okay, so roughly, if I want to think about graphical models as tensor networks or monoidal categories, we have that wires are the variables, the boxes are the factors at some fixed parameters, or because we're working in this really abstract category, instead of thinking of the boxes as being a particular tensor, we can think of it as a whole space of tensors. Yeah?
Sorry, that wasn't in the past. Could you explain again how to go from the Bayes network to the vector graph representation?
Sure. This one, right? Yeah, OK, thanks. OK, so here's a Bayesian network. There's an x, there's an arrow to y, an arrow from y to w, an arrow from x to z, and an arrow from z to w. So there's a notion of factor graph. Say it's easiest to think about for undirected graphical models. I just take all the clicks, and those are the factors. Right? For the Bayesian network, it's a little bit more complicated. There's a paper, or the first time I think this was written down, which was by Brendan Frey in 2003. And so this part is that paper, which just takes, I think it's in UAI. So you take the Bayesian network. If I have an arrow from x to y, I replace the arrow from x to y by an arrow with an explicit box in the middle, and that box is the factor. And that just represents the stochastic matrix that transitions from x to y, the conditional distribution. Similarly for x to z, and then since z and y both go into w, I have to marry the parents and represent it as a conditional that links these two because they have the same normalizing factor. And so that's this third box h, which is the third factor that appears in this thing. So that's the distribution, conditional distribution of w on the state of y and z. So that's the factor graph model. And then to convert the factor graph model to a string diagram in a monoidal category or tensor network, I have to explicitly put in the root distribution as a map from C to, or from the underlying field to a vector. So that's like just a vector representing the root distribution. I want to write all of the observed variables as wires hanging off of this thing because I want to connect it to this image of a tensor that I showed earlier where I think about it as wires coming off. So all 4 variables are observed, so they have wires sticking off of them. And that's it, really. Thank you. And similarly for the undirected case.
An arrow from y to x. Suppose your arrow was from y to x.
Yeah.
You put the root.
So yeah, then the root would show up over here instead.
But it could also show up in x.
Yeah, you could edit into. No, I think if the arrow went just this way.
No, both.
If it was both.
It's always root well defined.
Yeah, I mean it's your factorization of the Bayesian network. At some point you have to pick a place to start. That's the place where the root is. It's not there may be multiple parameterizations which give the same network. Yeah, equivalence classes. Yeah. And so if we really want to think about these things in terms of spaces, so if we want to ask this question, if I throw a Bayesian network at you and I say, what is the space of probability distributions this network could possibly represent, I can think about that either by saying, well, we have a parameter, we have all these parameters. The parameters somehow are sort of buried in this. The parameters are explicit in terms of certain types of factors which are allowed. Maybe they're the smaller dimensional than all possible factors. And then I can vary those factors and see what the space of tensors that are traced out is. Or I can actually think about, if I want to think about it abstractly, instead of being a vector space, I can attach to each of these things instead its own little variety or its own space of possible parameters, and then apply my composition and tensor product rules in order to get a description of the global space. Okay. Okay, so yeah, so boxes are the factors or the fixed parameters or spaces of factors. If we make some suitable assumptions, which won't be satisfied in the deep belief network, but which are satisfied in many of those submodels, global properties that we're interested in, like the space of probability distributions that can be represented, or the equations that cut out that space, because we need some representation of that space, can actually be computed by gluing together local information. Right? So that's kind of the ideal situation. All we need to know is what's happening at each piece and how they're attached together, and we can figure out the global structure. How do we describe these things? So we would like to, some kind of complete description of the space of representable probability distributions. So that's how we get into the last subject of today's lecture. So that was tensor networks. So if I want to describe spaces of probability distributions or spaces of things cut out by varieties or images of these type of nonlinear parameterization maps, algebraic geometry is the language that we have to use to describe that. So that's the last topic for today. Okay, so algebraic geometry, what is out? So this is going to be a 5-slide course in algebraic geometry. It's the study of solutions to systems of polynomial equations. That's the one-line answer. So what does that mean? So if I have a ring, something which is closed under multiplication, addition, things like that, some axioms that you probably learned and possibly forgot at some point. So I have a ring of multivariate polynomials. So I have just polynomials, complex coefficients. You could take real coefficients, rational coefficients, whatever you like, in some variables, x1 up to xn. Maybe these represent probabilities of n different outcomes. So here's an example of a polynomial, right? So I have a ring of multivariate polynomials. Each polynomial describes something. Any polynomial I pick in this ring, I can think about what is the zero locus. So what are the set of all points in C to the n or R to the n such that this polynomial vanishes on those points. It has the value 0 in those points. I can think about this as a space of equations. If I have blah, blah, blah equals blah, 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 I just subtract instead, right? So now I can just think about polynomials. I don't have to think about equations. And so this is really the generalization of sort of linear equations, systems of linear equations. Okay, any polynomial has a zero locus, the set of all things that vanish, or the set of all points at which that polynomial has value 0. This is the variety. The term is the variety cut out by this polynomial f. If I just have one polynomial, this variety, or an irreducible polynomial, this variety is going to be a hypersurface. Here's an example. So this is I have two variables, and I call them P1 and P2, and I can take the variety of V2 minus P1 squared, and that's going to be, and the real part of it is going to be a parabola. Right? So it's just, this is the kind of thing we have. This is a hypersurface. Hypersurface meaning it's one dimension, codimension one dimension less than the ambient space. Okay, so here's another example. Consider a restricted Boltzmann machine that has 4 visible and 2 hidden nodes. And it's binary. So it's a 16-dimensional space of probability distributions that it can represent. This one is a...
Why is it a 16-dimensional space?
Well, 15, but because this is R2, tensor R2, tensor R2, tensor R2, or 2 to the 4. And then I subtract 1 to get because there's a normalizing constant.
Can you explain that?
Sure. So this is a description of these are hidden and these are visible. I have a 2 by 2 by 2 by 2 table of numbers. Right? In each entry of this, and these have labels like P0110, which is the probability that I see fixing some parameters, the probability that I see 0110 as my bottom, as my output. Right? So pick some parameters. This defines a probability distribution, P110. So these are so as I flip each of these, there are 16 possible bit strings. They're the entries in this table. So there's
and you treat it as a vector space and then just normalize, because you can always normalize it.
Yeah, and then you normalize it so that the probabilities sum to 1. So this has 2 to the 4 parameters, or 2 to the 4 possible. It's a 2 to 4 dimensional space of things. If I just stretch it out and think of it as a vector space, and then I lose 1 because
6 variables?
Because of normalization.
How many variables there? 6 or 4? 15. Well,
How?
Graphical model.
There are 4 visible and 2 hidden. So it turns out that this thing is a hypersurface. It's another hypersurface. So there's some polynomial that that cuts out this space of distributions, which could possibly have come from an RBM with 4 visible and 2 hidden nodes. That polynomial is not nearly as nice as x minus y squared. It has degree 110, and it has probably around 5 trillion monomials. Okay. So these things can be extremely nasty, but nevertheless, we can know, in that sense, we sort of know what the space of distributions that are representable is. And that gives you a hint for how hard these things can be. Okay. So that's with one polynomial. Now suppose I have a whole set of polynomials. I have a system of polynomial equations, like a system of linear equations, but I'm allowed to square and cube and multiply things. I'd like to require that all of these polynomial equations hold simultaneously. That is, I'd like to require that, that all of the polynomials vanish, so we want to keep only the points where they all vanish. So we have a bunch of hypersurfaces. And so do we want the union or the intersection of those hypersurfaces? Okay, we want the intersection, right? So the place where all of those things agree. So we have now the zero locus, the points at which v1 up to vn in C, such that f of v is equal to 0 for all f and f of a set of polynomials. And this is called the variety determined by that set of polynomials. Okay. And that's the set of solutions to this system of polynomial equations. So that's varieties defined by sets of polynomials. I can go in the other direction. Given a variety or given just a subset, I can find the set of polynomials that describe it. So given a set S in C to the n, I can define the vanishing ideal of S as just the set of all polynomials in Cx1 up to Cxn, such that f of a, the polynomial applied to a, is 0 for all a that appears in this set S. Okay, so that's the vanishing ideal, and it's an ideal. So you have to prove that it's an ideal, and then Hilbert's basis theorem from over 100 years ago says that if I have such an ideal, it has a finite generating set. So there's some finite list of polynomials that describe such that all other polynomials can be written in terms of those. Okay, so that's nice. So it'd be bad if there were infinitely many. It would sort of be a hopeless task to try to describe a set of probability distributions this way. I can combine these operations. If I have a set in Cn, I can take its Zariski closure, which is start with the set, take all the polynomials that vanish on it, and then take all the points on which those polynomials vanish. So that's a closure, and I get a topology called the Zariski topology.
So I have a question from the past, I think, 2 slides ago. So, so that paper by telling you, is it actually just result for this RBM, or is it more general result, and you just they actually showed that every RBM has this polynomial and they give the number, the degree, and so on for every RBM?
Well, for this particular RBM,
just for the zero particular,
just this one with 4 visible and 2 hidden nodes.
So do we know if every architecture, it's obvious that every architecture has a corresponding polynomial?
Right, so every architecture has a system of polynomials.
Okay.
When we're lucky, the numbers work out such that we only need one. This is a case where we're lucky in that sense, but we're unlucky in the sense that it's an enormous polynomial. So one of the big things in this area is always to figure out efficient ways to describe these things so that you're not trying to write down 5 trillion. Yeah.
When you have a probability distribution, what is a polynomial here? So
It's a polynomial in the probabilities. So for example, that would be a polynomial in the probabilities. This one is degree 2, and it has 2 monomials. This is some polynomial in these probabilities, but there are 100, each one has degree 110. And we don't actually know what that polynomial is. So it's kind of an engineering problem to figure out that polynomial. One way to do it is to, well, you could write down a 5 trillion by 5 trillion matrix and take its kernel. Its kernel is one-dimensional. So it's just linear algebra. But it's a little hard to do that. Yeah.
In this example, the ambient space is the probability distributions over 4 binary
Exactly.
things, and that is 15-dimensional.
Right.
So how do you get that the probability, the subspace that you can represent in this way is 14-dimensional? Or it's not a subspace, but how do you?
Yeah, I mean, it requires proof. It's a little bit of work to do that. You can count parameters, and the parameter count works out to be the right number of parameters, but then you have to make sure that nothing sort of collapses or cancels. So you have to show that it's full dimensional, and that it's full dimensional, has the right number of parameters, that. So it's not that hard usually to prove that something's a hypersurface, but it's not immediately clear. Yeah.
So the 14 parameters are one for each line and then one for each circle.
Yeah. Okay. So this is our. Okay. So I work in this area. There's sort of a, there's an industry called applied algebraic geometry. Right? So this is most of applied math, or much of applied math for a long time was differential equations, sort of analysis, right, of various forms. And sort of another half of math is algebra and algebraic geometry. And so there's been a lot of work in the last sort of 10 years really using algebraic geometry to do various things. So why would we do applied algebraic geometry? So one reason is just this sort of bastardization of the magic statement. So any sufficiently advanced field of math sort of has enough structure to model any problem, really. So, okay, you can do it, but why should you? Algebraic geometry is sort of as old as it gets, and it has a lot of structure, so we should expect we'll be able to model lots of problems with it. You can actually even formally say that, make a formal statement about this statement, which is that there are problems in algebraic geometry, ideal membership. Many of the problems that we'll encounter can be reduced to this. So ideal membership is X space complete, and that covers a whole lot of computable things. But even worse, there's Mariuszewicz theorem, which says that every recursively enumerable set is a Diophantine set, which is the answer to Hilbert's 10th problem. And this is a question in algebraic geometry. So that basically says that any question that has a computable answer in the sense that it's recursively enumerable can be expressed somehow in terms of algebraic geometry. So this means that just about any question we can ask, we can somehow twist it into a question about algebraic geometry. Okay, sometimes that's of course useless to do, but if we do it right, and we're lucky, we get some geometric insight into the problem, right? So we had some complicated problem, and now we can talk about spaces of things and tangents and points, and we can actually think geometrically about what we're seeing. And if we're really lucky, some hammer that we've developed in algebraic geometry over the last 300 years will actually apply to that problem and help you figure out what's going on. So that's why we could expect to do this. Okay, so let's get a little bit more into the kind of trick we need to do to understand the space of probability distributions in a deep model or another probabilistic model. And this is something called implicitization. So we'd like to study this space of probability distributions, but we're not handed this model as a set of polynomials, right? We don't get a set of polynomials. We get a graph and a set of parameters. We get a parameterization map. So we get not the thing, but a map to the thing. And that's described by a graph. Each box in this tensor network that we've seen is allowed to take on a certain restricted set of values. So what we need to do is study this parameterization map, the map from the parameter space to the probability space. We want to understand this map. What is its image? Its image is the space of probability distributions this model can represent. Its fibers tell us things like, given a piece of data, I fit it to the model. Now, what are all the other parameters that could have explained that? If we're in a really nice situation, that was the only parameter that could have possibly explained it. But maybe we have a finite set of parameters that could have explained it, or we have a continuous space of parameters that could have explained it. And understanding that helps us understand our optimization procedures. If we get a complete description, we really succeed with our implicitization. We get the equations of this variety, so the equations that must vanish like this on this probability distribution, and we get the inequalities that a probability distribution must satisfy. So we get a complete test that says, test these finitely many things. If they're all 0, then it came from a DBN. If some of them are not 0, or some of the inequalities are violated, that it could not possibly have come from a DBN or other Bayes-Knit network. Okay, so that's the kind of thing we're going for. Let's be a little bit more careful about it. So we have a polynomial map, phi, that goes from a parameter space in Cn or Rn to an ambient space. So we like to work over C because it's algebraically closed, but we can often conclude things about R, even though we're working mostly in C. Okay, so here's our example. Here's a parameterization, x is equal to t, y is equal to t squared. This thing has fibers, it has an image. So it defines an image, fibers are very small, phi of the parameter space, which is inside of C to the M. And we'd like to know the implicitization, which is which equations define or cut out this set, so the image of this thing. And of course, you know the answer. It's y minus x squared equals 0. That's the polynomial that cuts out the image. Okay, so in this case, it's very easy. In general, it's very hard to figure out what this thing is. And one of the things we do when we pass from the image of the map to the equations that define it is we take a Zariski closure, right? So we missed some points or something. There's no way to account for that. We've taken all the equations that vanish on it. So even though it's just a small set, we've taken all the equations that vanish, and if we think about that now as all the points on which those equations vanish, we've taken the closure. Okay, so this process is called implicitization, and in general, it's really hard. Okay, so it's not going to lie to you, it's a tricky thing to do, and you can bang your head against the wall, but it's not impossible. So we sort of in this community started working on this in the last 15 years, and sort of year by year, the models fall, and we understand exactly what their space of probability distributions is. It's not impossible. You can write a thesis about it or something. Okay, so here's an example that we've already seen, this naive Bayes model or mixture of products. So we have some discrete node up here, we have some transition matrices, and let's talk about what kind of equations this guy can have. So some other names it goes by: naive Bayes model, mixture of products, secant variety of a Segre variety is what an algebraic geometer would call it, or set space of things with tensor rank, or border, the limits of points with tensor rank something. That's another name for it. Okay, so in the graphical model notation, one point is just a P1 or a probability or like a coin flip. Possible values for the possible biases for the coins. I can have 4 independent coins. That's a Segre variety inside of P15, which is, I'm thinking this is complex projective space, but you could think about it as the probability simplex on 4 binary variables. And the equations for this are just the 2x2 minors of the flattenings of a 2x2x2x2 tensor. So we already told you about what flattenings are. So that means I write this thing as a matrix. I take all the 2x2 determinants, and those cut out this space. So that's the independence model. So those are the things that I can use to test whether these 4 things are independent, right? And the distance from that independence model, is sort of like a chi-squared test. Then I could take the secant variety. So the secant variety, I have some variety, some set of points. I take a point on it, I take another point, and I take all the points on the line that come in between. That's the first secant variety. If I want the second secant variety, I get to take I take the plane spanned by this. Then I move these points around. That defines some set which contains the set I started with, and that's the secant variety. And that corresponds to taking a mixture. So the first secant variety says I have a binary hidden node up here, and then these are all binary too, but they don't have to be. So the first secant variety of a Segre variety is cut out by now. I take all the flattenings, and I take their 3x3 minors. So in this case, we're lucky. It's just like the matrix case. It's basically the condition that this thing is rank 2. But in general, we're not going to be this lucky. And we'd like to know a lot of basic information about this. So the most basic piece of information we can ask for is the dimension. So we can answer questions like, is this a hypersurface? Then we'd like to know the equations and the degree, and we'd like to know inequalities and lots more and more and more detail. Right? Okay. The dimension is kind of the first question we can ask. Okay, so we have some tools to do this other than paper and pencil. So there are computational tools that are available in algebraic geometry. I just want to mention some of these. And many of the times when we're trying to figure these things out, we mix computational experiments with theory. So we run the program and ask it what the equations of this thing is, and it tells us. And so then we can do that for a bunch of small examples, and then we make a conjecture as to what it is for all sizes. And most of this is powered by Grosvenor basis methods, Singular, Macaulay 2, Cocoa. And they work on symbolic term rewriting, and they use this nasty algorithm, which is doubly exponential in the worst case, which is why we can only do very small examples. But if you're lucky, you can do big examples. But if you're unlucky, it's quite bad. Okay, so then you can do various, you can transform the problem into a polyhedral problem, which was used to compute the things that I was telling you about before in this Kyoto and Yu paper. And we burn a lot of hours. This is probably a very small number for you guys, but sort of in my group, it's my clusters. People are anxious to hear what my results are to report to NSF because I burn a lot of their CPU hours looking for answers to problems like this. Okay, so there's also this new trick called numerical algebraic geometry, which is a strategy for approximating solutions of polynomial systems by doing this sort of numerical path following or homotopy continuation. And this is kind of an exciting new thing that allows us to get approximate answers, but to scale beyond the things that the symbolic methods can do. We can find points and scale to thousands of variables for certain problems. So usually the other stuff runs out around 10 or 16 or 30 variables is maybe as far as you can go. So you can only do small examples. This can get bigger. So there's some software to do that. Okay, so this is the last slide I think I'll do for today. So why are our geometers interested in this stuff? So that's these applications in statistics, machine learning, complexity, things like that have revived a lot of the classical viewpoints like invariant theory that people used to study 100 years ago. There were a lot of problems that have been open for 100 years were now getting solved because people are starting to care about them again. And we're getting to sort of reclimb the hierarchy of tools that have been developed in geometry over the years, the Italian school, the formalisms of Zariski and Serre and Grothendieck as we put these problems together and recast them in a more sophisticated way. And finally, these problems have really revealed gaps in our knowledge and pushed us to do new theoretical developments and new computational tools to deal with these sort of large objects that are high dimensional, have lots of symmetries, and oftentimes these things smooth out. Okay, so I'm running low on time, so I think I'm going to stop there for today and we'll continue in the morning. Thank you.